Greetings. This is class 4 of the DC controls sequence of classes, and today's topic is breaker failure schemes. Before we dive into that, I want to give you a safety tip, and today's safety tip is what to do if you are in a substation and you accidentally trip a circuit breaker. And this is would be a really unfortunate thing to have happen. Fortunately, it's not happened to me. However, I do know people that it has happened to, and what you do if you do accidentally trip a breaker, number one thing, do not close it back in. There should be somewhere in the control building a phone number to call for local dispatch. You need to call them, you need to tell them exactly what happened, and you need to follow their instructions precisely. And most likely their instructions will be something like, get the hell out of my substation. But anyway, kidding aside, do what they tell you to do and be forthright and upfront about it. And although people may be a little upset at the time, I assure you that they will ultimately be forgiving. All right, today's topic is breaker failure schemes. And we're going to start by looking at how we back up circuit breakers and radial systems. Then we're going to go through basic breaker failure logic and tripping. And I'm going to conclude with a lesson learned from a project I did many years ago about breaker failure schemes and how they can actually turn around and bite you a little bit. Okay, the first thing I want to cover is how we back up breakers in radial systems. Okay, what I've drawn here is a basic radial system, relatively simple concept. We have a source. In this case, I've drawn it like you would have in a distribution substation, where you've got a transformer, you're going to come off it, you'll be a main breaker, and then a distribution bus with a series of feeder breakers coming off of that bus. Now, typically on these, since power flow can only go one direction, it's not a transmission system. It's actually relatively simple to protect, and you generally do it by coordinated overcurrent relays. You have 50-51s, which are inverse time and instantaneous overcurrent settings, and you just set the feeder breaker to trip a little bit faster than the main breaker. Pretty simple, and in some cases there have actually been schemes to speed this process up, where instead of allowing a 5 to 10 cycle lag between the two, you just allow like a 2 or 3 cycle lag. But as this relay sees that fault and starts to trip this breaker, at the same time it sends a blocking signal to this relay telling it not to trip. And then at that point this would continue to look at the fault, but it would do it with a slower response time. Again, if there are any questions on this or anything else in this class, please refer them to your department manager. And if you can't get a good answer that way, you can always email me at eric.hale@poweringe.com. This scheme right here that I just described to you is actually very similar to the one that you would be protecting, say, your house, or branch circuit in your house. If you have a fault on that and its branch circuit breaker isn't able to clear it, then the next breaker upstream would do that with a presumed bit of a lag behind it. You can also get a similar concept to this in metal-clad switchgear. Now, I describe this as being a typical of a distribution substation. Picture, instead of open air rack, you had this as metal-clad, and you're trying to protect this from both faults on the feeder and faults on the bus. And anyone that's not familiar with arc flash dangers really should I'd like you to spend a little bit of time on YouTube, Google it, and listen to some of the horrific stories that people have gone through that have been exposed to arc flash. I mean, we use arc flashes to melt steel in steel mills, so you can imagine what they do to human flesh. All of this is relatively simple, but what would happen if we get rid of this? Don't make it radial system, and now say you could put power this way as well as coming down this. Well, that's what the situation that we have on the transmission system, and that's where we have to go next. Okay, the purpose of a breaker failure scheme is to isolate a failed breaker and try to localize that problem within that particular substation. Speed is essential because system stability is at risk. Typically, your limit on how long your transmission system can sustain a fault without risking a voltage collapse that can lead to tripping off all of your generation in a regional outage is right around the zone 2 time delay in your line relaying scheme, and we'll cover that next week. Typically, for breaker failure time delays, we limit that to half of the zone 2 time delay. And again, so this is going to put it on the order of 10 cycles. So say you have a line fault and you detect it and try to trip your breaker and try to accomplish that within 4 or 5 cycles, and it doesn't work. Well, about at the 10 cycle point, you're going to trip all of the breakers outside of, or all the adjacent breakers, to assure that you have de-energized that fault. Now, the causes of these things are actually fairly numerous. Probably the number one cause of a breaker failure is some problem within the DC circuit. And we've spent quite a bit of time going through that. And you can imagine that if someone were to, say, leave a test switch open, or a branch circuit breaker on your DC panel either tripped or was inadvertently left in the open position, well, your breaker certainly is not going to work. You can also have mechanical failures within the breaker, say a pole, something breaks and a pole actually does not, the interrupter doesn't actually get moved when you try and trip the breaker. You can also have insulation failures within the circuit breaker, and if the insulation fails, well, you can do all you want with the interrupter, and it's really going to have very little effect. Testing errors are a huge problem with breaker failure schemes. And quite a few utilities will go to great lengths in how they design the schemes to make it easy to be tested and safe to be tested. And the example I'm going to give you at the end of this lecture was caused by a testing error. So anyway, another consideration as we go through with this. Now then, spend a bit of time and talk about what I mean by tripping adjacent breakers. And now think back to when we were talking about the zones of protection. And this is a very similar concept to that. I've shown up here a substation that's basically 2 rows of breaker and a half, and I've got a transmission line coming out of one and then a transformer coming out of the other. And say we have a fault on this transmission line, so to clear the fault we would trip these 2 breakers. Okay? Well, what happens if this breaker fails to open? We go into breaker failure, and then we have to trip the adjacent breakers, which means you're going to have to de-energize the fault with this breaker down here. Now, this would be a main bus, and if you happen to have something connected to that main bus, it will also be de-energized when you trip this breaker. Now, over on this side I've shown a transformer and low side circuit breaker there, and 2 breakers on the high side. And say there's a fault within that zone of protection, so we have to trip these 2 breakers and this low side breaker. Okay, what happens if one of those does not trip? Well, say it's this breaker that fails to trip. Well, then we're going to trip the adjacents, and we've already tripped the low side. But say going back to here, say our fault is out on the line, and we try to trip these 2 circuit breakers, but this one does not trip. Say something's wrong with it, it just sits there. The breaker failure scheme will then have to trip this breaker, and it's going to have to go to the low side of that transformer and trip it to completely de-energize the circuit. Now, similarly, I'll leave you with this thought. Same concept. We go to trip, say we've got a fault in this zone of protection, and that breaker fails. We're going to have to trip this circuit breaker, but we're also going to have to trip the other end of this transmission line. And that's called a breaker failure transfer trip. And we're going to cover that here in a couple classes. Okay, one of the key components of a breaker failure scheme is the time delay relay, or the time delay function. These typically go by the acronym TDPU or TDDO, and that's time delay on pickup or time delay on dropout. These are just like the 95 auxiliary relays, very, very simple relay, except that there is a definite and very precise time delay either when the relay will pick up or drop out, so that you go and you close the contact to energize the coil, and say you've got it set for 10 cycles, it will not change state for 10 cycles. But then say there's a dropout delay on it, it's changed state, then you remove the source of voltage to its coil, it will stay picked up for that dropout delay. Okay, here's how we depict that in logic diagram form. It's basically just a rectangle and an input and an output, and your pickup delay is shown here, and your dropout delay is shown here. And then it's actually a really good practice right below it to write what unit of time you're dealing with here. Because it could be seconds, it could be cycles, it could be milliseconds. For various applications, you could all want that. And so it's a really convenient practice to put that right below that symbology. Okay, now I want to shift gears and actually talk about breaker failure logic. What I have shown on the screen here is, in its fundamental state, breaker failure logic. And how this works, the 50 BF, 50 is an instantaneous overcurrent, so as soon as your current goes up to the threshold that you can say for sure that's fault current, you're going to pick up that contact. And then, because you only want your breaker failure scheme to work when you truly have faults on the system in general. Now there's an exception to that I'm going to cover here, kind of a philosophical thing that some utilities practice. But in general, you want to only have this happen when there are faults. Now then, the next contact down is BFI, or breaker failure initiate. Anything that will cause a protective trip for that circuit breaker, you want to take another contact from that and run it into your breaker failure scheme. So if there's a lockout relay, you're going to take one A contact to trip the breaker, and another A contact is going to go into your breaker failure scheme. Similarly, if you have, say, a line relay, a 21 or a 67, that is going to trip the breaker, you similarly will wire a second contact to the breaker failure scheme to initiate breaker failure. Now, as soon as both of those pick up, you're going to start your timer. And think about this. That timer is going to give you 10 cycles to de-energize that fault and make the 50 BF drop out. Otherwise, you're going to have the output contact, because that's a time delay on pickup. You're going to have that output contact, that 62 BF, close, and then you're going to trip your lockout relay, and at that point you're going to trip all the adjacent circuit breakers, and that's usually a pretty big deal. And again, typical breaker failure time delay is around 10 cycles. It can be a little less, and just as a good rule of thumb, it's going to be right around half of your zone 2 time delay. Okay, in a Boolean way of looking at this, or Boolean equations, you can summarize this in two simple equations. 50 BF and BFI equals 62 BF, then 62 BF equals 86 BF. if you remember nothing else out of this class, I want you to remember this. Okay, breaker failure initiates. Let's spend a little bit more time talking about those. All protective trips initiate breaker failure. However, control trips do not. So you're not going to wire a contact from your control switch or from SCADA to initiate breaker failure. Okay, there are actually two types of BFIs if you think about it. And one of my clients differentiates these as a BFH and a BFL. And what those are, the BFL is for the few kinds of faults out there, such as a sudden pressure relay in a transformer, that may not actually be associated with fault current. It's unlikely, but it is possible. And in the old days, not too many people would worry about this because it took so many various discrete devices to implement a breaker failure scheme that they generally liked to keep these things simple. But with modern programmable relays, it gives us a lot more opportunity to really fine tune and finally design how we design these schemes. And so here in a couple classes, I'll show you an example of a breaker failure scheme that actually takes this into account. Another thing that your breaker failure scheme can do is initiate a retrip. And what a retrip is, if you've got two trip coils and you wire all your protective trips to trip coil 1, and then through a different DC source, you take a contact from your breaker failure relay, and as soon as you get a BFI in the relay, you'll immediately trip coil 2 out of a different DC source. And remember what I said a few minutes ago, one of the most common causes of a failed breaker is some problem with the DC source. And this recognizes it, and I think this is a really cool, really slick approach to improve the certainty that your breakers will trip when called upon. Okay, again, adjacent circuit breakers, you got to make sure that you're tripping your low sides of your transformers and the far ends of your transmission lines. And on the transmission line part, again, we will cover that in a couple of classes. Okay, what I've got on the screen is a breaker. It's actually it has more on it than breaker failure, and I'll be covering this particular drawing in the 7th class in this sequence. But the way this thing works, right over on this side is the actual circuit breaker that we're tripping, and all of our BFIs in this are located right over here. And then this is the logic that we use to program the relay. Again, the formats of these things, every utility will have a different format, and but what's important is that you understand the basic concepts behind it. And so when you see a drawing like this, particularly one you're unfamiliar with, you can take these basic building blocks, go through it, and understand how the scheme works, and then do design work on it. Really fundamental to what we do for our clients. Okay, one last concept I want to leave you with. This is the normal breaker failure logic that I've shown you. And I came up with this a few years ago. I had a client who, for their breaker control scheme, they would block operate for the breaker for low gas. So obviously you're not going to allow the breaker to close for low gas, but you're also not going to allow it to trip. And their concern is that if you have a trip, there'll be enough arcing inside of the cylinder that holds the interrupter that's going to increase your chances of having a flashover and actually damage the breaker. So anyway, they had that logic designed into their circuit breaker. But here's the rub in that. If you've got that 63G relay picked up, you know that breaker is not going to trip. Guaranteed. And so there's really no point in going through the breaker failure time delay. And what this scheme does, what this scheme does is it bypasses that. So as soon as you see fault current and you have a breaker failure initiate, this contact's already closed, you will immediately, without time delay, go into breaker failure and trip all of your adjacent breakers. You may as well, because you're going there anyhow. All right, I want to conclude this class with a story about a breaker failure incident that happened on one of my projects many, many years ago. And I think there's a lot of value in just passing along stories, particularly ones that really illustrate key principles in our design philosophies. All right, to give it a little geographic context, this is the state of Oregon, and this is the greater Portland area. And over on the west side of town, the main source within Portland General Electric's system is St. Mary's Substation. And I'm kind of zooming in on it right now. And what you'll see if you look closely at this, in the middle you've got three big transformer banks, each of them about 250 MVA. You have a control building right here. And on this side you have a couple rows, a breaker and a half, although the last two, there's breakers missing, so you really just have double bus, double breaker. But anyhow, as we were converting this substation from its old configuration, which was a main and transfer scheme that dated back to the early 50s. And there are three transmission lines that provide power to the 230 system. This one right here goes to the old Trojan nuclear plant that's about 50 miles away, and it is a very weak source. It's not nearly strong enough to support the west side of Portland. This line goes to about 3 miles to Bonneville Power substation, and it's a very strong source. And then there's a transmission line that goes out this direction that goes to another Portland General substation, and it is equally strong, so that either of these two lines can carry the full load of the substation under most circumstances. We were about 6 months into this project, and we'd already started construction on the site, and someone realized that the configuration that the utility had prescribed to us had a flaw in it. And the flaw is this circuit breaker right here. If that breaker were to go into breaker failure, you lose the line to BPA Keeler, and you lose the line to Sherwood Substation, so you lose both of your strong sources. After much hand-wringing and deliberation, and it was going to be a big problem because if we decided to reconfigure this, we were going to have to slide these transmission lines down, and you can see that the existing transmission tower, no way could that support moving these lines further down. We would actually have had to gone and put in another big double circuit 230 line, or 230 turning structure. So again, after a lot of hand-wringing and deliberation, we decided to simply leave it as it is. And we figured that the chances that that breaker would ever go into breaker failure were amazingly remote. 2 years later, heard on the news and got a phone call that there had been a testing error. A relay tech had been working on that breaker failure relay, had accidentally left a test switch closed that should have been open, and lo and behold, they tripped that breaker. They lost the line to Keeler, the line to Sherwood, and this line doesn't have the capacity to hold the load at that time, and they ended up blacking out for about 10 or 15 minutes the entire west side of the greater Portland area. Now then, included in the facilities that were outaged were most of Intel's chip fabs that are within just a mile or two of this substation, and Nike's headquarters that's also about 2 miles from the station. Really unfortunate thing, hasn't happened again since. I'm sure they've taken additional precautions to prevent this, but it illustrates what can happen to you if your breaker failure scheme is subject to a testing error and you've put a common point of failure into your design. Okay, in this, to conclude this class, this kind of wraps up our study of circuit breaker schematic design, and we did that by concluding our discussion with breaker failure schemes and how we back up circuit breakers. All circuit breakers on the transmission system have to have a backup plan. And on the transmission system, we refer to that as breaker failure relaying. In fact, it's all circuit breakers in general have to have backup, not just the big fancy high voltage ones. So anyhow, this concludes our study of breaker control, and in the next class we will start studying line relaying. Thank you for your attention, and we'll see you in the next class.